Hello. So in this video, I wanted to set up a goal for us in calculus. Our goal is to be able to find the slope at one point. And this is what we're going to spend our time thinking about in this video. We thought about it a little bit in the previous videos with tangent lines and how there seems to be this kind of direction, this direction of the tangent line at every point that seems to suggest a slope, but we haven't really gotten kind of a mathematical way of expressing that. So we want to find the slope at one point, because I'm going to start this video by saying that there is one. There is a rate that can be attributed to each point. This is something you have to accept. Every point has just this number, which is the slope at that point, the slope of the tangent line at that point, that points essentially in the direction or represents some rate of change at that very moment. But what does that mean exactly? Let's say we have this space shuttle here, and the space shuttle is traveling outside of the atmosphere, so there's no drag. So it can just travel freely, and it turns on its engines, starts accelerating up, and right here, it just shuts off its engines. And if you're familiar with inertia from physics, you'll know that from then on, it will just keep moving at the speed that it was moving at when it shut off its engines. So, it just keeps moving, right? So we can just keeps moving in a straight line in terms of the speed. The speed just becomes constant, like that. But what just happened here? Because at this moment, we shut off our engines. At this moment, we shut off our engines. And then we started traveling in a straight line. And our speed was constant during this time after we shut off our engines. So we can just measure, if we take some, T1, let's say that's T2, D2 for the distance and the time, and T1, D1, we can just say that the speed after the space shuttle shut off its engines is D2 minus D1 over T2 minus T1. This is going to be our speed, which I'm just going to call V. So that's really interesting, right? Because, well, why is that interesting? Look, we found the rate of change of the space shuttle, and we can say, well, let's see. If there is a rate of change at every point, we know that throughout everywhere between these 2 points, it's moving at a constant speed. So we can just say at any point, it's moving at this speed, V, D2 minus D1 over T2 minus T1. But what else can we say? This moment, when we cut off our engines, we were traveling along this curve. We cut off the engines, and then we just kept moving at the speed that we were moving at when we cut off the engines. That says something really interesting, because this slope here, this slope that we found here, this is our slope, because we're doing distance and time, it's speed, but it really is just slope, is going to actually represent that, right? The speed at that point. Because, think, we could cut off the engines at any point, and if we cut off the engines down here, what would we do? We wouldn't move up like that, we'd move like that. The point is, you can cut off your engines, and then you have to keep moving at the same speed you were traveling at, so you can isolate what speed you were traveling at the moment in time when you cut off your engines, a speed at one point. So that's really just kind of a physical way of thinking of it, just kind of justifying that idea that there is speed at every point, because at every point you could, if you're describing a space shuttle, or, but this goes for everything to some degree, at any one point, you can just, cut off your engines in quotation marks and just start traveling in a straight line that would represent the slope at that one point. You'd start traveling a straight line at some slope, so there must be a slope at that one point when you stopped. Again, this is just a way in physics to think about it, but I found it really interesting, so I wanted to share it. But let's move on to how we can try to actually isolate that point, rather than just thinking about it and accepting it as a thing, right? Slopes at every point. Alright, so hopefully now you have the idea that there is a slope attributable to every point on a line, just a rate of change at every point of the whatever's on our y-axis relative to the x-axis, or any axes that we use. The y and the x are just if they're representing our function and what we're taking the slope of. And now I want to look at some cars. We have a car. This is our car here. This car is in traffic. This is probably like LA traffic or something. And we have this graph here of our car's travels, where y is the distance that we travel, just in any direction, and x is the time that it took. So let's say in this kind of traffic-y area, it ended up taking us about 2 hours to complete our trip, and let's say we went 40 miles. Alright, so I mean, this graph is already pretty suggestive. It looks like we started driving here, we got to go pretty fast here, but then we slowed down a lot. But then we sped up a tiny bit, and then it looks like we reached our destination, maybe. So we could suggest, maybe during this period there's a lot of traffic. That seems to make enough sense. But when we look at this point, what can we say? We can say, oh, what was our average speed over the entire trip? If we don't have a speedometer, what can we say about our speed? We can say, oh, well, from the start to 2 hours in, we went 40 miles total. So our average together is the total distance traveled divided by the total time. It's just going to be 40 divided by 2 miles per hour. We could combine that if you want, which is just going to be 20 miles per hour. That's just our average over the whole time. And that's how you have to think about the secant line. The secant line really is just an average rate of change, because isn't that what an average is? If an average of all of these different values exists, then the average times how many values those are should total up to the sum of all of those values, which is, in this case, 40 miles per hour. So all of those values that this is an average of, this is an average of the rate of change. This is the average rate of change, right? If we multiply 20 miles per hour times 2 hours, we're going to get 40 miles. And that's why it's the average rate of change. But think about what that says, average rate of change. If there's a rate of change at every point, which I just told you there is, let's use a good color for that. There's just a rate of change at every point, and I'm just going to use an arrow. Then you can think of this line as just an average of all of the infinite number of slopes at all of those infinite number of points. And that's a really interesting way of thinking of things, and that'll be important in a moment and in the next couple of videos. Now then, how does that help, right? Because let's say we choose a point, we want to know well, first of all, let's get rid of these arrows, they're not helping. Let's say we want to know how fast we're going right here. We didn't have a speedometer, we don't know. So how can we possibly get closer, at least, to knowing how fast we are going then? Well, go back to what we said before with the average. Over this entire trip, we got much faster, we got slower. There's a high kind of diversity of speeds here. We slowed down and sped up a lot. So what if we just change how many of these different speeds at all these different times we're averaging out with this line here? What if we just narrow our interval Because right now, we're measuring over 2 hours and we find this average. What if instead we measure around this point, say, I don't know, let's say that's 1 hour. Let's say that's 1 hour. All right, so let's mark this up. Ooh, that changes a lot now, doesn't it? Because if we connect these, look how much less that slope is than our one over here. That's not 20 miles per hour. That's like, let's say, that looks like maybe it's, I don't know, 2 miles over an hour. That's our slope, 2 miles over 1 hour, rise over run. This is 1 hour. So there's a difference of 2 miles. We went in this whole 1 hour. We're going 20 miles per hour here. And wow, that makes a big difference. If we just knew about the average of 20 miles per hour, that we'd think, oh, that's okay, I guess. But now that we know about this 1 hour of only going 2 miles, this 2 miles per hour, we learn a lot more about the situation. Now we know about the traffic. And now we kind of know about how fast we were probably moving around there. But we're still not 100% accurate, because if we just zoom in on this spot here, I'm just going to pull this out. If we just zoom in, we have our little curve here. And we have some, let's say we have some red point here, some red point here, and these are connected. But they still don't fit our curve exactly, right? It looks like right here, we're actually probably moving a little bit faster than that. And then right here, we were probably actually moving a bit slower than that. And right here. So we're still not perfect, right? Because let's say our point is this one here. We know kind of pretty close to there what around the speeds were. Close to that one, but we still don't know what the speed is at that point. So, I don't know, let's make it smaller. And as you'll see, as we make these intervals smaller and smaller, we're reducing the number of speeds that we're averaging out, and in turn you can think of reducing how many, the variance of the speeds within that interval, so that we can kind of say, when we have a line, we know all of the speed is constant, so all points have the same speed. But when we have a curve, we know that there's some average speed, and all points contribute to that average. But if we use less and less points in the average, maybe we can get an idea of the slope at each of those points. The problem is there's an infinite number of points, right? There's a point here, there's a point, this point here, there's a point here, there's a point here, there's a point here. They're all over the place. There's an infinite number of them. So it's not like we can reduce this interval to just include one point, right? Well, stay tuned, and we're going to start looking at this a bit more mathematically and trying to find that slope at one point in the next video. I hope this was clear. Thanks for watching. Goodbye.